Greetings. Let's say in this one we want to focus on abstract algebra, and the concrete example that we're going to be asked is, let's say we have some group denoted when we have like G sub n, and that's cyclic. So we have G sub n being cyclic, and we know that its magnitude, its order, the amount of its elements, is going to equal to n. So for example, if we want a cyclic group of order 5, it will be G5 and so on. And let's say that we can make Cartesian products, which are something like this: Gn times Gm. So that would mean that we have a Cartesian product of like a two-tuple where we have AB, and A is inside the Gn and B is inside the Gm. So it's basically this equals to all the two-tuples such that A spans Gn and B spans Gm. So all the combinations where A is one of the elements of Gn and B is one of the elements of the second group G sub m, well, where the G sub m of course has m elements and is cyclic, and G sub n has n elements and is cyclic. And now we are asked a concrete question. So let's say we have 4 options: A, B, C, and D, and we are asked which one of them is not cyclic. Which of the following Cartesian products is not cyclic? So let's say G15 times, I say times, but what I mean is the Cartesian product of G15 with G13, or G2 times G3, or this one, or this one. Now we are asked which of them is not cyclic. So this one is a Cartesian product of G15 with G13, G2 with G3, and so on. And all we know about that G sub some number is it's a cyclic group of that order of the number, that number states the order of that group, and that it's cyclic. So the G15, G13 both are cyclic groups. And the definition of a cyclic group is there's one element called the generator, and applying it with itself under the group's operation repeatedly will generate all the remaining element of that group. Then that group is called cyclic. And the idea here is we are asking which of these Cartesian products, because a cyclic group can be a group of numbers or Cartesian products, which of them is not cyclic? Which of these groups has no two-tuple AB in the form AB as I showed here, that such that this two-tuple, when applied to it with itself under the group's operation, I'll state what the group's operation is in a second, which of them will not result in generating all other elements of that Cartesian product? Which of the Cartesian products has no two-tuple among its elements, because its elements are the two-tuples? Which of them has no two-tuple that will, in operation with itself, generate all the other two-tuples of this Cartesian product group? This group made of Cartesian products of this defined kind. And, well, this is a thing that we should look at, because let's say that by G5 we say, oh, it's additive group of modulo n, of modulo 5, so G5 additive group of modulo 5. And of course cyclic can be generated, for example, by 1, but also by some other numbers. And G15 we will see as cyclic additive group modulo 15 with addition modulo 15 as the operation. And with Cartesian products, how we see the operation is very simple. We just take this number and use the modulo by this number when adding some elements inside it. So G15 consists of 0 through 14, G13 consists of 0 through 12, and when we are adding A, B plus CD. Now let's say I'm talking about A, G15 by G13. CD, what it results in is A plus C, B plus D, but this is mod 15 here, and this is mod 13. Of course, I could generalize it by not using this concrete example of 15 and 13, but you see, it will be 2 and 3 for the next one, 7 and 5, 15 and 10 for the next ones, respectively. So that's the point, that's how it works, that's the operation of these groups. Now we're asking, which of them will not be cyclic? Which of them will not have this? Well, the rule is quite simple. The rule is basically, as long as these two numbers, this one, and this one are co-prime, it works. It's a cyclic group as a Cartesian product. So these two, the 15, 13, are co-prime. 2 and 3 are also co-prime. Or co-prime meaning they have no higher common divisor than basically 1. Okay. 2, 3 is also fine. 7, 5 also co-prime. But 15 and 10, well, they have a common divisor of 1, but also of 5. So they are not co-prime. So G15 by G10 will not work. And there's a theorem, and I won't go into the proof, or a fact that one can realize. You can try with numbers, or we could also write out a proof. But basically the idea goes as follows. If you have some GM by, so the answer is D, all right? Answer is D. D of these 4 Cartesian products is the only group that's not cyclic, all right? So G times Gn. If we have this, it will be a cyclic, is a cyclic group if the GCD of M and N equals 1, which is a different way to say M and N are co-prime. If they are not co-prime, it won't work. Now, also a big idea is any non-zero two-tuple we take from that respective group can be A, B, C, or D. Let's say for A, B, C, or D, we can take 1 and 1 or something different, I mean, or anything. I mean, I can take 1 and 3 for, let's say I'm talking about A. It will, by being multiplied or added to itself, in other words, modulo 15 for the first entry and modulo 13 for the second entry, it will generate all possible two-tuples. That means it will be all the different combinations where this goes from 0 to 14, this goes from 0 to 12, because it's G15, G13. So it will generate. And any two-tuple of this kind, I mean, it could be 2, 5, it will also generate the whole group. The only two tuples that don't generate it is when one of the entries is 0, because then it stays at 0, no matter how many times it's multiplied, or added to itself, in other words. So we're doing this addition modulo N and M, N and M respectively, and yeah, so that will not work if we are dealing with a 0 in the two tuple. So unless it's a 0, it works. So I mean, then you can count how many elements has this group. By the way, it's very simple to count the elements of this Cartesian product group. It's always the two numbers multiplied, 15 times 13 in this case. So it's 195 elements here. And then we can subtract all the elements that contain a 0 in either entry. And when we subtract that from 195, we have the amount of elements that are generators. So all those different elements, any of them, one of them we can choose and add it to itself to generate all the remaining elements of this whole group, right? 0, 1, 0, 2, 0, 3 until 0, 13, then 1, 1, 0, 1, 0 until 0, 12, because we have 0 to 12 for G13 and 0 to 14 for G15. So 0, 0, 0, 1, 0, 2 until 0, 12, then 1, 0, 1, 1, 1, 2 until 1, 12, and then we go like this until it's 14 on the first entry and again 12 on the second entry. So all these combinations. And yeah, so that works if they're co-prime. But if they're not co-prime, you can find out it doesn't work. I mean, this is not a proof, but I'm taking an example. If I say I will use the generator, and this is a generator that would definitely work for the other three as long as it fits inside the elements of those other three groups. So for example, it would work for G7 by G5, G15 by G13, because it is small enough number for them. So let's say 5 and 2. 5 is element of G15, 2 is element of G13, or so 5 is element of G7 and 2 is element of G5. So for both A and C, it would definitely work. I mean, in B it would not work only because 5 is higher than the G2. G2 only has 0 and 1, but I mean, I could choose 1, 1 as a generator, and it will still work for the other three. It would only not work for this one. Okay, so 5, 2. How does it work? For all the other ones, well, just try it and it will generate it all. But for D, it won't. Okay, so I do 5, 2, and again, when adding it to itself, I will always do modulo 15 and modulo 10 respectively for the two entries now, because I'm dealing with D. I'm showing that by this 5, 2, I cannot generate D, so it doesn't work like the other groups. So 5, 2, and then that's the first case. Okay, I generated 5, 2 itself by itself, add it twice to itself, so 10, 4. I mean, it doesn't surpass the order of the two groups in the cross product, so it's not shown yet, but 3 times. Well, I have 15 and 6, but 15 modulo 15 is 0, so I'm back at 0, so I have 0, 6. Okay, and 4 times I get 5 and 8. So the second entry is still developing to different numbers, but the left one will only oscillate. If I have a 5, it will oscillate between 0, 5, maybe 10, but that's it. Okay, it won't have other values. Okay, multiples of 5, modulo 15 will always result in 0, 5, 10, right? So one will not get like 13, but we need that because in G15 there is a number 13. So that's a problem, and we see D will not have, this generator won't work, but the opposite is true for the previous 3, okay, which we said are actually cyclic, because we can take any non-zero two-tuple and it will generate. Okay, I will not write it out here, but you can verify it numerically with yourself, and it does work out.